Hello everyone, my name is Anas Sheikh. I am a student of Vishwakarma University Pune pursuing Masters of Computer Application, and today we'll dive into the world of linked list, a core concept in data structure and algorithms. Data structures are essential building blocks in computer science, defining how data is organized, stored, and manipulated in a program. Understanding data structure is a key to developing efficient algorithms as they provide the foundation for efficient data management. Data structures can be categorized as linear and nonlinear. Linear structure like arrays, stacks, queues, and linked lists store elements sequentially, while nonlinear structures like trees and graphs have more complex relationships. Linked lists belong to the linear group but differ because of their flexible memory allocation. This flexibility is what makes them powerful in situations where data changes frequently. Linked list is a linear data structure where elements called nodes are not stored in a continuous block of memory. Instead, each node contains two parts, the data itself and a pointer to the next node in the sequence. Imagine each node as a train car linked by couplings. Each car holds a piece of information and knows how to reach the next car. Because linked lists are not restricted by memory locations like arrays, they allow for dynamic memory allocation. This flexibility is a key in situations where amount of data changes frequently, as we can add or remove nodes without having to shift all other elements like an array. Let's see the types of linked lists. There are different types of linked lists, each with a unique way of connecting nodes. The main type includes the singly linked list, doubly linked list, circular linked list, and doubly circular linked list. Each type has specific advantages depending on the application's need for traversal direction and memory efficiency. Each type of linked list has its unique strengths like flexibility and data manipulation or efficient memory use. A singly linked list is one of the most straightforward types of linked list. In this structure, each node has two main parts, the data it holds and a pointer to the next node in the sequence. The first node in the list is called the head, and the last node points to the null, indicating the end of the list. One key feature of singly linked list is that they allow traversal in only one direction, from the head node toward the end. This makes them memory efficient as each node only needs a single pointer, but it also limits their flexibility. Unlike arrays, singly linked lists do not require a contiguous block of memory, so they are ideal when we need to manage dynamic data efficiently. For example, singly linked lists are commonly used in applications like stacks and queues, where we only need to access data sequentially. Although singly linked lists are easy to implement and manage, they have some limitations. We can't traverse backward, and accessing specific nodes requires going through each node in sequence from the head. This limitation can make certain operations like finding or deleting a node in the middle of the list slower compared to other data structures. A doubly linked list is a more advanced type of linked list that builds on functionality of singly linked list. In doubly linked list, each node contains three components, the data itself, a pointer to the next node, and a pointer to the previous node. This setup allows traversal in both directions, forward and backward, making it more versatile than a singly linked list. With a doubly linked list, we can start from the head and move toward the end, or beginning at the end and move back to the head, making it useful for scenarios where bidirectional access is required. This two-way traversal is advantageous in applications like navigation systems where we might need to move both forward and backward within a sequence of items, while the extra pointer for each node makes doubly linked list more flexible. It also requires more memory compared to singly linked list. Each node holds an additional pointer which increases the memory footprint. Moreover, since each node has both next and previous pointers, insertion and deletion in a doubly linked list require adjusting two pointers for each neighboring node rather than just one. However, these operations are still relatively efficient as we don't need to shift other elements as would be necessary in array. Circular linked list is a unique type of linked list where the last node doesn't point to the null. Instead, it points back to the first node in the list, creating a continuous circular structure. In this type of list, there is no true beginning or end, which allows for continuous traversal of the list without needing to restart. Circular linked list can be either singly or doubly linked, but they share the common characteristics of circularity. For example, in a singly circular linked list, each node has a pointer to the next node, with the last node looping back to the first. In a doubly circular linked list, each node also has a pointer to the previous node, with both ends connecting to create full circle. This structure is useful in applications where a continuous loop of data is beneficial, such as in round robin scheduling where each process needs to be accessed in a repeating sequence, or in applications like multiplayer games where players take turns repeatedly. Circular linked lists are also valuable in implementing data structures such as queues, particularly for tasks that involve repeated cycles. A doubly circular linked list is an advanced type of linked list that combines the feature of both doubly and circular linked list. In this structure, each node has three components: the data, a pointer to the next node, and a pointer to the previous node. Additionally, the last node in the list connects back to the first node, and the first node's previous pointer links to the last node, forming a complete circular chain. This two-way circular connection allows for seamless traversal is both forward and backward direction without a defined start or end. Doubly circular linked lists are useful for applications that require bidirectional navigation with continuous looping, such as in certain operating system process where task or operation might loop endlessly. This structure also works well in applications like music playlist or photo slideshows where user might want to cycle forward and backward continuously through items without reaching an endpoint. Linked list offers several advantages that make them useful in wide range of applications. First one is dynamic memory allocation. Unlike arrays, linked lists don't require a predefined size. We can add or remove nodes as needed, making them ideal for scenarios where memory needs change dynamically. This flexibility ensures we use only the memory we need, which can be particularly important in systems with limited resources. Second one is efficient insertion and deletion. In linked list, adding or removing elements doesn't require shifting other elements as it would in an array. We simply adjust the pointers of the nodes. This makes linked list especially efficient for frequent insertions and deletions, particularly at the beginning or end of the list. Next one is foundation for more complex data structures. Linked list serves as a base for other complex data structures such as stacks, queues, and even hash tables and graphs. These structures build upon linked lists to manage data effectively for various specialized operations. Memory usage in unpredictable scenarios. In systems where memory usage is unpredictable or where memory allocation is frequently changing, such as in garbage collection or memory management systems, linked lists provide an efficient solution. They allow memory to be used dynamically, reducing waste. While linked lists offer significant advantages, they also come with certain drawbacks. First one is increased memory usage. Each node in a linked list requires extra memory for a pointer or two pointers in case of doubly linked list. This can add up, especially with large lists, and may make linked lists less memory efficient than arrays, which only stores data. Second one is no direct access to elements. Unlike arrays, linked lists don't allow constant time access to elements. To find a specific item, we must start from the head node and traverse the list, which can make searching or accessing elements slower, particularly in long lists. Extra operations during traversal. Linked lists require additional pointer adjustments when inserting or deleting nodes, especially in doubly linked list or circular linked list. These extra operations can increase the complexity of certain operations compared to arrays. Next one is increased risk of memory leaks. Since linked lists are dynamic memory allocations, there is a higher risk of memory leaks if nodes are not properly deleted when no longer needed. Proper memory management is crucial when working with linked lists to avoid wasting memory. Linked lists are highly versatile and have various practical applications, particularly in scenarios that require dynamic memory management. Here are some key use cases. First one, dynamic memory allocation. Linked lists are commonly used in systems where memory allocation needs to be flexible, such as in operating system. Since linked lists allow for dynamic resizing, they are ideal for tasks where memory requirements change frequently. Next one is building blocks for advanced data structures. Linked lists serve as a foundation for other data structures like stacks, queues, hash tables, and graphs. For example, a stack can be implemented using a linked list where nodes are added and removed from the head, maintaining efficient last in first out behavior. Third one is garbage collection. Linked lists are used in memory management and garbage collection routines to track memory that's no longer in use. By linking freed memory blocks, linked lists allow for efficient reuse of memory, helping to reduce memory fragmentation in systems with dynamic allocation. Fourth one is real-time applications. Linked lists are also useful in applications like task scheduling and real-time data processing, where tasks or data may need to be processed in a sequence, but the exact number or order of elements can change dynamically. Thank you for your attention. I hope this presentation has clarified how linked lists work and why they are such a valuable tool in data structures and algorithms.